Welcome to the second revision workshop on work, energy and power. And in particular, in this workshop, I'm going to focus on power. Now, power is certainly not the main focus of this section on work, energy and power in the grade 12 syllabus, but this is what is required. And so one does need to focus on this as well, because there are questions, and sometimes these long questions that are asked that require you to be able to apply your knowledge of power. So first things first, the definition of power. So according to the exam study guidelines, the definition of power that you need to use is that power is the rate at which work is done or energy is expended. Now, that is a pretty standard definition of power that we use throughout the grades. And the basic formula for power, as you would have learned in lower grades, is that power is the work done per unit time. The exam study guidelines state that you need to be able to calculate the power involved when work is done, perform calculations using P average as force multiplied by the average velocity when an object moves at a constant speed along a rough horizontal surface or a rough inclined plane, and then calculate the power output for a pump lifting a mass, lifting water, for example, through a height, and notice at a constant speed. So we're going to come back to that. I'm going to discuss all of these aspects. So first things first, let's talk about power. So power is work per unit time. So it's the rate at which work is done or the rate at which energy is transferred. Now, if one is looking at a system where there is a pump, then there is a non-conservative force that is being applied, namely the force of the pump on the column of liquid that is being pushed up. So we would be working with the work done by a non-conservative force. If, for instance, you're dealing with a problem like this, where an object is being pulled by means of a cable up a slope, then the motor is applying a force, a non-conservative force. Remember, an applied force, a tension force, these are all non-conservative forces. They don't conserve mechanical energy. They change the mechanical energy. In this case, you would see that the motor would be increasing the potential energy. So the change in potential energy would be greater than zero because it's increasing in height. And if it's accelerating and the velocity at the bottom of the slope is smaller than the velocity at the top of the slope, then the change in kinetic energy would be greater than zero. If, however, it is being pulled up at a constant velocity, then the change in velocity would be zero and the change in kinetic energy would be zero. Then the work done by the non-conservative force would only be a change in potential energy. So you will see later on when we come back to this that the crate is moving up at a constant speed, which negates the change in kinetic energy. So if we now use what we've learned in the first revision workshop, that WNC is equal to the change in potential energy plus the change in kinetic energy per unit time, and if we work with a force, a non-conservative force, an applied force, which could also be a tension, that is working in the direction of the change in position, then, and that's normally the case, normally with a pumping system or a motor, the applied force is in the direction that you want the object to move, then using the fact that the work done is force times delta x, cos the angle between them. Remember, what we're doing now is we're using the fundamental definition or relationship here. What we're doing is we're using this here It comes from that the work done by the force is equal to the magnitude of the applied force, the change in position, delta x, and cos theta. And if the angle is 0 degrees between the force and delta x, then the work done by that force is going to be F delta x over, and of course it's delta t, that's the work done. F delta x cos 0 is 1, and over delta t, notice that delta x over delta t gives us our average velocity. And that is where that formula comes from, that P average equals F, and it is V average. So you can use a bar on the top, that line on the top, the bar, or you can write it as V average. Now, if we are working with a system where we are dealing with a pump, right? And obviously pumping systems can be much more complex than this. We're going to assume that the pump is at the bottom and it's a bore roll and it's pushing a column of liquid up, right? Then the height of the water column is called the head. This is actually called the delivery head. In pumping systems, there's often a suction head, but they're not going to go into that level of detail. So if you look at this, we have, if you had the water being accelerated by the pump, you have a V initial and that V final is different, then you're going to get a change in velocity and you would get a change in kinetic energy. But if V initial and V final are equal, which is what they will do in the syllabus, if they give you a pumping system, they are going to give you a pump that's pumping water at a constant velocity. Well, then your change in kinetic energy is 0, right? So now you will see that the work done by the non-conservative force is the change in potential energy over the change in time. The change in potential energy will be greater than 0 because it will pump the water up to a higher height. So the change in height will be positive. So the change in potential energy will be positive. So therefore, the change in potential energy, which is mass times gravity times the change in height, is going to be over delta T. And the M over delta T gives us the mass delivered per unit time. And so this is often what they give you. So if we look here, when it comes to power, if we're dealing with a pumping system, we could be working with something like this, where you're given the rate of delivery, the amount of volume per unit time, or the amount of mass of water per unit time. We'll still look at that, times G times the change in height. Or we could also be working with a system which could not be a pumping system, could be like, for instance, this, where you have a force that is acting in the direction of a change in position, as is the case here. You have a tension force pulling the object up in the same direction. Well, then you could be working with the applied force, the non-conservative force, times the average velocity. We will look at that a little later. But let's go back to pumps, right? So if we go back to pumps, one of the things I want to mention to you is that when you're dealing with a column of water above the pump, right, that column of water has a mass. Obviously, water is very heavy. We're going to be looking basically at pumping water. You could also be pumping things like oil, which we are not going to be looking at in the syllabus. We basically be bore rolls, pumping water. Then the force of gravity is obviously the weight. So this column of water is pulled to the center of the earth by the gravitational field. So the weight is mass times gravity. So if you're going to have a pump that is pumping the water at a constant velocity, then the water applied by the pump on the water must be equal in magnitude to the weight. Otherwise, you would get an acceleration. So if we look here, if we look at the force of the pump, so the force of the pump that would be also equal to mass times gravity. That would be the applied force. We're obviously simplifying it. In the real world, the water gets accelerated, but we're keeping it simple. So the force that the pump applies on the water, which we've represented there, we've drawn a free body diagram of the water, has got to be equal in magnitude to the weight of the water. So therefore, we have the work done by force applied over delta T is going to be the power of the pump. Now, things can get very complicated. We're not going to worry about what's on the left here. That is efficiency. So let's take a look at an example. Right. So we have a system where we have and I've made this a little bit more difficult than you would probably get in an exam. I have brought in efficiency, right? Practice harder than you need to play. Let's take a look at this. We have got a pump that is sucking water and pumping water from here all the way up to there. Now, the height through which it pulls the water is 1.5 meters. The height through which it delivers the water is 20.2 meters. So the total height of delivery, the total changing height will be 21.7 meters. Right. So I'm looking at a more sort of real world problem where there's a section of the pipe where the water is sucked. They call that the suction head. And there's a section of the pipe above the pump where the water is delivered. That's called the delivery head, head being height. So the sum of the two gives you the total head, the total height, the change in height. All right, we are going to, and this is not, they're not going to give you this, where there's a change in velocity. All right, but let's look at it. V initial is 0 meters per second. V final is 4.5 meters per second at the top there. And this symbol represents the diameter. Okay. So the diameter, the inside diameter of the pipe is 150 mils. The flow rate is 2.5 cubic meters per minute. Right, so I really am adding everything here. All right. So you will definitely not get a problem as difficult as this with all the elements that I've got here, but practice harder than you need to play. If you can understand this, then whatever you get in the exam is probably going to be easier. So if the flow rate, if 2.5 cubic meters of water flows out of the pipe, is delivered per minute, then the question is calculate the power rating of the pump, all right? And you're told that muddy water, so they're pumping muddy water here, has a density of 1,105 kilograms per cubic meter. All right, so let's calculate the power rating of the pump. So if we look at the theoretical power of the pump, it's the work done by the non-conservative force, which will be the force of the pump, over the time interval. All right, we are going to work per minute, so we're going to work in 60 seconds because we want to work with watts or kilowatts, so you've got to work with per time. The work done by the non-conservative force is delta EP plus delta EK. Notice that they haven't given us the average force that the pump applies on the water. So therefore, we are working with the changing potential energy and the changing kinetic energy. Now, the work done by the non-conservative force equals the change in potential energy, mass times gravity times the change in height. That's the total height through which the water is pumped. Plus, now, according to the syllabus, this would be naught because there would be a constant velocity. We are working with a more general case where there is going to be an acceleration of the water, which is more what occurs in reality. So it's a half m, v final squared minus v initial squared. Now, the mass, how much water, if you've got 2.5 cubic meters being pumped per minute, how much does 2.5 cubic meters of muddy water, what's its weight? What is this mass? Well, using what you've learned in GET, that density is mass over volume, mass is density times volume. So mass is going to be the density of the muddy water times the volume. Well, they told us it's 2.5 cubic meters. So 1105 times 2.5 gives us 2,672.5 kilograms. we have the mass of water that's pumped per minute. Just want to mention to you that if it's pure water, clean water, it's 1,000 kilograms per cubic meter. So now substituting in there, we've got the 2,622.5 kilograms times 9,8 times the total delivery height of 21,7 meters. Remember, we're looking at the total height through which the water is pumped from the inlet to the outlet of the pumping system. Right, so we look at that, we say, okay, that's 21,7 meters, half the mass, 2,762.5 times. Now, the final velocity at the outlet is 4.5 meters per second, and you square that minus the initial velocity. We assume the water is stationary, all right, that's 0. And when you work that out, the power output is 10,257.393 watts. That is the power required to pump that amount of water theoretically. But now, your pump only has an 82% efficiency, which is the case in the real world. Nothing works perfectly. So if theoretically you need to have a power output of 10,257.393 watts to pump 2.5 cubic meters of muddy water per minute, then does your pump need to be less or more powerful than that? It needs to be more powerful. You need a higher power rating than that. So therefore, we now use, if you look here, your power output, right, that's what's required. That is what is needed to pump 2.5 cubic meters of muddy water per minute. All right, your power in needs to be more. So the efficiency, we use eta, the Greek letter eta, over 100 is your power output over your power input. Your efficiency is 82 over 100. Your power out is the theoretical power, 10,257.393 watts, right? But in actual fact, you need more than that. So the power in is at the bottom. We make that the subject of the formula. Notice that now your efficiency of 82%, 0.82, is actually sitting in the denominator, which is going to make your answer bigger. So your power in is 12,509.016 watts. So your power rating, what your pump needs to be, is approximately 12.51 kilowatt rating. Now, this is a much more difficult pump problem than what you'll get. It includes efficiency. It includes a change in kinetic energy of the water. However, the chances are that you're not going to get an efficiency calculation, but if you do, well, now you know how to do that. And that this is going to be 0 because your constant velocity means there's no change in your velocity between when the water comes in and when the water leaves. So the work done by the pump is purely to move the water from the suction to the delivery part of the pumping system. So now that we've done that, I want to now move to where we are dealing with a system like this, where we have a motor pulling a crate of mass 300 kilograms with a constant force by means of a light, inextensible rope. That means that the rope doesn't stretch. So in other words, if this is moving at 1.5 meters per second, this is moving at 0.5, that's moving at 0.5, that's moving at 0.5. There's no one part of the system moving faster than the other. It says over a light frictionless pulley, so that means the tension to the left and the tension to the right of the pulley in the rope is going to be the same, or in the cable. Right? It says light frictionless pulley, so we're not going to have to worry about any dynamic or rotational kinematic effects. That is what we do at university. The coefficient of friction between the crate and the surface of the plane is 0.19. You are going to have to work with friction here. It says, calculate the magnitude of the frictional force acting between the crate and the surface of the inclined plane. All right, so we've got a 25-degree angle and 300 kilograms. So if we look at that, I'm going to go to the right here. I'm going to draw a free body diagram. We're going to have the weight of the crate. There it is, W. The weight is going to be mass times gravity, which is going to give us 300 kilograms times 9.8 meters per second squared. Just going to get my calculator. So that's going to be 300 times 9.8, and that gives us 2,940 newtons. Right, that is obviously, there's going to be two components. There's going to be a parallel component, and there's going to be a perpendicular component. And if this is 30 degrees, sorry, it's not 30 degrees, it's 25 degrees. If this is 25 degrees, then W parallel is going to be, if you look here, if that's W parallel, that's 25, then this angle is always 25. That's the angle between the weight and the perpendicular. So this is going to be W perpendicular over W is going to be adjacent over hypotenuse. That is going to be cos, but W parallel over W is going to be opposite over hypotenuse. This is 90 degrees. So this is going to give us W parallel over W is going to be sine 25. Opposite over hypotenuse is sine 25. So W parallel is going to be 2940 multiply by W on both sides. W is 2940 times sine 25 degrees. So the parallel component of the weight is going to be that times sine 25. And that's going to give us 1,242,498 newtons. Remember, we try to round off to a minimum of 3 decimal places, even though the NSC requires only 2 decimal places, just to keep it safe. W perpendicular is obviously going to be the W cos 25, so this is going to be 2940 cos 25 degrees. So if we've got here 2940 multiplied by cos 25, and that's going to give us that W perpendicular is 2664,545 newtons. 2664,545. Right. So it's always good to take the weight on a slope, take the weight, work out the weight, take the components, W parallel and W perpendicular, and work them out separately before you go any further. We know that there's going to be a normal reaction, right? And because of the nature of the system, this cable is pulling parallel to the slope, so there's no component of the tension force in here. There will be a tension force in here. There's no component of the tension force that is anything else other than parallel to the slope. So there's no perpendicular component. So there's nothing in this tension that's going to change, going to add or take away from the interaction between the slope and the block. So therefore, we know that it's basically just the tension force that is applied there. The normal reaction is going to equal, W perpendicular. The normal reaction is going to equal W perpendicular, right? Because there's no other force or component of a force that is perpendicular to the slope. So we know that the normal is going to equal W perpendicular. Apologies for that. It's just busy saving. Right, so it's going to equal W perpendicular, and that's going to be W perpendicular we worked out as 2,664,545 newtons. Okay, so N equals W perpendicular. We worked out that W perpendicular is 2,664,545 newtons. Now, because the motion is up the slope, and you will see that it's going to be at a constant speed. So the velocity is going to be 5 meters per second, and it's going to move up, right? So the velocity is going to, the magnitude of the velocity is going to equal the speed because it's in a straight line, right? That's 5 meters per second. So therefore, the friction is going to be in the opposite direction to motion. Always is. So therefore, the friction is going to act down the plane, right? So the tension is up the plane. W parallel is always down the incline, and the friction force always opposes the motion, which is up the plane. So the friction is going to be kinetic friction. So the kinetic friction is going to be mu k, the coefficient of kinetic friction, times the normal reaction, which is basically an indicator of the interaction between the two, how much the plane needs to push on the block to support it perpendicular to the plane. Right, we're told that the coefficient was 0.19, the coefficient of kinetic friction is 0.19. Right, so we say, okay, that's great. So this is going to be 0.19 multiplied by the normal reaction, which is 2,664,545 newtons. Right, so we've got that. And then we can say, all right, so we've got this, and we multiply by 0.19. And that gives us that the kinetic friction is 506,264 newtons. So it's 506,264 newtons, right? So now, if we look there, we see, okay, we have now answered. So calculate the magnitude of the frictional force acting between the crate and the surface of the inclined plane. Right, so if you look at that for 3 marks, obviously there's a mark there because they've asked for the magnitude. They haven't asked for in the opposite direction to motion or down the plane. Right, there was the normal force would be a mark, and I would assume there would be a mark for the formula. So that is 3 marks. It's a fair amount of work for 3 marks, but that's one of the areas where the NSC makes things a little bit more difficult. Now, if you look at the next part, it says calculate the average power delivered by the motor while pulling the crate up the incline. Now, a 6 marker in NSC is telling you that there's a little bit of thought that needs to go into this, and there needs to be a little bit of application and synthesis. So if we look at the average power delivered, right, we are looking at the power delivered by the motor. There's no mention of inefficiency. So if we look here, we can say, well, okay, the average power is going to be, now remember we've got WNC over delta T, but wait a minute, we also have, apologies for this is what happens when you have your device connected to other devices. All right, I do apologize for that. So power average is equal to the applied force of the pump. Now, the pump applies a force, not a pump, sorry, my apologies, the motor. The motor applies a force on the rope. There is force applied. Right, remember force applied. Right? The force applied creates a tension. There's a tension force there, and there's a tension force there. Because of the fact that the pulley is frictionless, the tension on this side and the tension on that side is going to be the same. So in actual fact, the tension force is the applied force. The applied force of the motor is transmitted by means of the tension force to the 300 kilograms. We also know that we actually have the average velocity because the velocity is constant. So the average velocity is 5 meters per second because it doesn't change. So we have that. And we know that through discussion that the tension is going to be the applied force times V average. We have that. So we need the tension force. And this is where our free body diagram helps us. So you're not explicitly asked to draw a free body diagram, but free body diagrams are your biggest friend in dynamic problems like this. So we are now going to work and say, okay, if we look here, we can see parallel to the slope, we have the tension moving up the slope, we have W parallel and FK moving down the slope. Now, because there is a constant velocity, there's no resultant force on the slope. So therefore, the tension is going to be equal in magnitude to W parallel plus FK. So we can say, okay, so if we want to, we can solve T on the separately. We can say T equals W parallel plus Fk. So therefore, the tension is going to equal W parallel. Now, fortunately, we've worked out W parallel, 1,242, 1,242,498. There we go, 1,242 plus 1,242,498 plus Fk, right? And I can maybe just move this over a little bit. That would be great, right? So you can maybe can't move that too much. Let's move this a little bit here. Okay, sorry, I just want to move this a bit. Okay, right, so we have that plus Fk, so Fk is going to be plus, sorry, just moving my calculation here slightly. It's 506,264, right? So therefore, we can say, okay, adding those two together, we get that the tension is 1,748,762 newtons. And so that is the force. This here is the force that's applied to the block to move it up at a constant velocity. Now that we have that, we can now substitute this into there. So we can now say, okay, so opening it up here, P average is going to be the tension force, 1,748,762 newtons. And that's going to be multiplied by the average velocity. And the average velocity we know is the speed, 5 meters per second. And remember, power is not a vector, right? So we don't have to worry about directions. So times this by 0.5, and we get that the average power is 874,381. Now, what is the unit? 874,381 watts. And so, if we look at mark allocation, I would say that you would probably have a mark for W parallel. You would have a mark for the formula, So that's 2. There would be probably 2 marks here, 3, 4, and then here would be 5, 6. So we have covered the 2 basic types of problems you could be asked in an exam situation. The one is, and the more likely one is with like this, where you are asked to work with the average power on a slope, where an object is moving at a constant velocity. They could ask you where the object is being accelerated, highly unlikely, where it would start at the bottom of the slope at 0, and at the top of the slope they would have to give you the velocity, let's say 2 meters per second. Then the average would be the initial plus the final over 2. So 0 plus 2 over 2 would give you 1. They could do that, okay, but more often than not, they just give you a constant velocity. Right. The other type of problem is obviously the pump problem, and I would like to believe that after having covered these 2 problems, that you should be well prepared for anything that you encounter in your prelim exam or your final exam that involves power in a mechanical system. So I wish you all the best with your preparation for your prelims, and I will post this recording at a later stage. Thank you.